So we're looking at how we create these numbers. And the name of this number is called, or this method is called, this is factorial. Whenever you have that exclamation point. And you said that when you typed that in your calculator, you came up with 120. Let's discover what that factorial is doing. So why don't you play around and see if you can figure out what's going on, what the calculator is doing behind the scenes to create that 120. So explore by typing in other numbers and see if you can find the pattern. Has anybody found a pattern yet? Except for it gets really big really quick. Let's try a couple of numbers and see what happens whenever we try these numbers. So what is 1 factorial? 2 factorial. 3 factorial. 4 factorial. And then we found 5 factorial to be 120, right? So let's see if we can figure out how they've made it through this progression. So now that 2 factorial is at 2. How could I have gone from 1 to 2? I could have either added 1, I could times by 2. What do I do to get to 6? I could add 4 or times by 3. What do you think it is, Shelby?
So, like, the answer for 2,
Uh-huh.
if you do the 2 times the 3 down there, you get 6. And then 6 times 4, and then 24 times 5.
And then, so this one we multiply to get 6 factorial and multiply it times 6. And give us 720. And so that's exactly what's going on. We're multiplying it times all the previous. Or more specifically, all previous numbers. Because that's all those other numbers are, is the previous numbers before them, right? So 4, 3, 2, 1. And you can see why this is going to get really big really quickly. So we're going to multiply 7 factorial. We'll put a 7 in front of it. And so this is kind of like the exponential growth idea. We're continuing to grow ridiculously fast. But let's look at this. We had 2 factorial times 3 factorial. That means I have 2 times 1, and then 3 times 2 times 1. And again, you could do this in your calculator. And that would give me 2 times 6, which is 12. 5 factorial, 5 times 4 times 3. Wait a minute, if I keep going, I can just represent that by 3 factorial, right? Those can cancel just like a normal multiplication and give you 20. When you're dividing factorials and your numerator is bigger than your denominator, you're never going to have a fraction. It's one nice thing is you're always going to be able to cancel things out. So we're going to be studying today, we're going to be looking into Pascal's triangle and the binomial theorem. And so we're going to be looking at some statistics. All of these are based upon probability. This is something that was covered for y'all back in 7th, 8th grade. I can't remember which grade level I taught it in. And now Pascal's triangle was not covered then, but the probability this is all based upon was covered in those years. But I am not so focused in Algebra 2 on you doing it by hand. You can use your calculator, because we're using that to go farther. I want you to take some time at your table. I want you to look at Pascal's triangle, which is what this triangle is. there are tons of patterns that exist inside it. I want y'all to see if you can find any patterns that are showing up here. So anybody have any ideas of some of the patterns that exist here? They don't have to be complex ones. What is the outside number going to be each time? That's a pattern.
5, 4, 3, 2, 1.
Oh, that there's going to be a, let me get my mouse to behave. What other patterns do y'all see?
10, 6, 3.
10, 6, 3. What pattern is that? I'm not saying you're not right. I just, what pattern are you seeing? As I'm,
It's going by a 4, 3, 2. Like that. Going
2,
by 5, or,
3.
2, 3, 4.
So you're the first one to get that one. Any other patterns? Pete, don't be afraid to say it. There's a really basic one that y'all are missing.
Like, I don't know how to explain it. Like, if you add these two together on all of them, it equals the bottom, the one under it, like the row under it.
Okay, so let me highlight and see if I'm talking, see what you're saying. So you're saying if I take these two numbers and I add them, it equals this number,
Yes, on the like the whole thing.
the whole thing. That's how Pascal's triangle is developed. You found how Pascal's triangle is developed. So now we're answering A and B. I can't remember what question A was, but through our discussion, we've been, I think it was y'all finding the patterns. So write down some of the patterns that we've discovered. So like the outside row is always 1. The second row down is counting by ones. The next row down is counting 2, 3, 4, 5. That triangle is made up of the two top numbers adding to create the bottom number. And it may be you don't write it in words, you may describe it up there on the picture. And then what we're going to do is we're going to create n equals 6, which is our row 7, but it's called n equals 6. Because we're starting counting at 0. And that's important to note. And so I want y'all to try to create this row 7 and then n equals 7, which would be our row 8. I want you to create that row spot as well. So go ahead and check your work with what I have here. Is it still following those same patterns? Well, let's look at that. One, I think it was you, Shelby, that talked about it's increasing on that third row down. So we increase, and so is it continuing to increase by one more each time? So we increased by 2, increased by 3, 4, 5,
Oh, yeah.
6.
That was Josh.
Oh, it's Josh. Sorry. Can't remember who it was that came up with it, but it was. And so that third row is still continuing to increase like that. And so we are going to take and use this triangle throughout most of our lessons. So you're going to have it to where you can flip back to look at. Okay? It will show up, but it's not going to have all the rows unless you go back to look at this one. So Brianna loves hockey, and she's so obsessed with hockey that she decided to draw hockey sticks around the numbers on the Pascal's triangle. Lo and behold, she found a pattern. What is her pattern? So in the purple boxes are her patterns. What did she observe?
She added all the numbers in like the straight rows to get the bottom at the bottom.
So the long part of it, the sum of that equals the bottom number. Okay, let's see if we can come up with 2 more hockey sticks and see if they follow the pattern. So we have one here. And they're continuing to follow that pattern. Oops. So all the hockey sticks I drew followed that pattern. And you may have even drawn that pattern here. So that's A and B underneath that number 1. And now let's look at Drew and Latasha's Pascal triangle. Drew came up with the idea, and we don't know if either one of these are right, so some of these may be a bad idea. He says that if you take 2 to the nth power, and n being the row where we start off counting at 0, hence us having this pattern written over here. So 2 to the first, or 2 to the 0, 2 to the first, 2 to the second, and it would equal the sum of those numbers. Is that true or false? And don't just check those 2, check farther down. So like 2 to the 5th, is that equal to the sum? True or false? Is he right or wrong? If he's wrong, tell me how you know he's wrong. If he's right, tell me an example of how you know he's right. So what is 2 to the 5th power? 32. So let's see what the adding of that row is. We have 20 plus, and I'm just kind of looking at going from center out. This is 20, and we add in 10 more, so that's 30 plus 2. That matched up. Here we had 1 plus 2 plus 1. That gave us 4, which is 2 squared. 2 cubed is 8. 3 plus 3 is 6, plus 2 is 8. And you'll notice that pattern is going to keep checking out. Letitia looked at it a little bit different. She said, excluding this spot, if I alternate signs, so positive, negative, positive, negative, positive, positive, negative, positive, negative, and add it across, then it would always end up basically canceling each other out. Is she true or false? We'll always end up with a sum of 0, she says. So what's the sum of n equals 2 row? 1 minus 2 plus 1. Zero. 1 minus 3 plus 3 minus 1. 1 minus 4, negative 3 plus 6, positive 3, minus 4, negative 1, plus 1. 0. So we're continuing to get 0 each time we add. So Pascal's triangle is going to have many uses. And it's used to explore and calculate probabilities, as well as multiply out binomials. Binomials, two things in a parenthesis being added or subtracted, raised to a power. So let's kind of go through a few of these. A plus B to the 0 power. Anything to the 0 power is A plus B to the first power means it's itself. This is going to go back to some math that we had done earlier this chapter where we had found out that to be a squared is equal plus 2ab plus b squared. And then I am going to, instead of us taking time to multiply these out, I'm going to go ahead and give you what these will be multiplied out. A cubed plus 3a squared b plus 3ab squared plus b squared, or b cubed, excuse me. And this one is a to the 4th power plus 4a cubed b plus 6a squared b squared plus 4ab cubed plus b to the 4th. So again, I told you we're going to be using Pascal's triangle. I want you to compare this to Pascal's triangle and see what is the connection between what we just did and Pascal's triangle. What are my coefficients? Do these show up anywhere? So if I look at my n equals 4 row, the numbers are 1, 4, 6, 4, 1. 1, 4, 6, 4, 1. I look at my n equals 3 row, it is 1, 3, 3, 1. 1, 3, 3, 1. So my coefficients follow that Pascal's triangle. That's how you're going to answer A. What's happening to my exponents as I progress across going to the right on my A's? What's happening each time?
Goes down by one. Or down.
My A exponent decreases by 1. But what happens to my B exponent?
Increases.
Okay.
So it just moves it over to the B.
So basically we're taking 1A and putting it over with a B. So we start with A to the 4th. We now have A cubed B. So you're talking about how it just moves it over. So that means that we're keeping a constant sum of our exponent of 4 each time. Where is that 4 coming from?
Exponent for the
And so you know that those exponents are going to combine to equal 4. So if I had a 6th power, those exponents are going to combine to be that 6th power. So I want y'all to take this time, and I want you to expand each binomial, and I'm going to let you see the answers as we go through it, using Pascal's triangle, and that's that rows that we created. These two, B and C, are from the rows we created. A is from previous, the last row they created. And I want you to see if you can find what the expansion is going to be. Check your answer A. So in case you need it, I'm going to walk you through B again and kind of talking about it. So we talked about that our exponent on A is slowly decreasing. And I'm leaving room for me to write other things here because I know that's not the only thing that's happening there. My B is increasing. So the first one didn't have 1. The second one had 1. And then if I go through and I look at my numbers, it would be 1, 6, 15, and we're adding it each time. 20, 15, 6, 1. And again, that came from n equals 6 row of the Pascal's triangle. And so that's what you should have had for C. So as you can see, these start getting longer and longer each time we go down. And so there's a shortcut way of handling it. So if I don't want to take and find everything, and I want to find a specific location, we can use the binomial theorem to help us find specific locations inside the pattern. So we can look for the third term, the fourth term, the fifth term, whatever it may be, and not actually have to take and find the entire expansion. And so before we can do that, we need to talk about what this is. So when you have in parentheses, a n over a k, or a number over another number without a fraction bar, that's another way of writing like 4 combination 2. And if I was to work this out, what that means is I have 4 factorial divided by 2 factorial times 4 minus 2 factorial. So 4 factorial means I have 4 times 3 times 2 times 1. 2 factorial, 2 times 1. 4 minus 2 is 2 factorial. Well, all that is this. And so I'm left with 12 divided by 2, which is 6. Let's see if we can figure out how to do this in your calculator. So I want you to look through it, and I'll give you a hint. We're talking about, at the beginning of the lesson, I talked to you that when we talk about probabilities, and more specifically, this is called a combination. So how can I get my calculator to find this number 6 for me with me just being able to type it in? Where would I need to look? So go into your calculations page, go to your main menu, find probability. What button is probability at? So type in the 5. What one is combination? And so on your main page, it's going to go NCR when you do that, and it's going to open a parenthesis. I can't remember, it may do this where it opens and closes it. In this space here, you're going to write 4, 2, and that will give you, when you press enter, that'll give you 6. Find A and B. Anybody have the number for number 5, combination 1? What about 7, combination 4? And so for you to remember kind of what this goes back to your 7th, 8th grade when you were talking about combinations. And you said, okay, there were 7 people trying out for being a committee member. And there are 2 people on the committee. How many different ways can this group be formed? Or Sonic loves to use this one. They said they used to advertise they have so many different combinations of drinks. It was using this format. And so we can use this to expand a binomial using the binomial theorem. This top number is going to be your power. The bottom number is the term minus 1. And that also is your power on your b. Those will always match. So this is the first term of the sequence, second term, third term, fourth term. And this is how you can actually find it whenever you're like, okay, I'm raising some a plus b to the 150th power. I want to know what the 100th term is. So you do, okay, the top number is 150. The bottom number is 100 minus 1, which is 99. B is to the 99th power. Therefore, what would A have to be to? What power would A have to be to? Because remember, these have to add up to be 150. So it would have to be 51. And then that would be the 100th term without having to do the entire process. Other than that, Pascal's triangle is usually the easiest way. So if you're just trying to find a certain term, then the binomial theorem is the easiest way. But if you're trying to do the other, go with Pascal's triangle theorem. And so I'm going to show you it with the binomial theorem down here so you can follow through my process. So my power is 4. So 4 combination 0. I'm going to take my 3x and I'm going to raise it to the 4th power. Then I'm going to get to my next term. 4 combination 1. Take my 3x, raise it to the 3rd power, but now my y has gotten to the power of 1. But I'm going to take my 4 combination 2, my 3x raised to the 2nd power, and then the y squared. 4 combination 3, 3x to the 1st power, y cubed. 4 combination 4, we have 3x to the 0 power, y to the 4th. So 4 combination 0 would give us a 1. 3 to the 4th power, that's the same thing as 3 squared times 3 squared. So 9x to the 4th. I keep doing that. 81x to the 4th is 9 times 9 is 81. Plus 4 combination 1 would give you a 4. 3 to the 3rd power is 27x cubed. Y. What is 4 combination 2? What did we say it was earlier? Six. 3x squared means it's going to be 3 times 3, 9x squared, y squared. Plus 4 times 3 to the x, y cubed, plus 1 y to the 4th.
How many times?
And so when we look at this, we're going to multiply that out. 1 times 81 is 81 x to the 4th. 4 times 27 is 108 x cubed y. 9 times 6 is 54 x squared y cubed, or y squared. 12x y cubed and y to the fourth. So it's hard to see it here that follows a Pascal's triangle, but you have to look at it before you expand it out. These numbers are the numbers that came from that Pascal's triangle on n equals 4. So you can use either method. Like I said, the binomial is great if you're trying to find a specific term. Y'all's homework is to do B.